Morning to all. So, in this today lecture, we want to see about the transient response analysis of the electrical circuits. So, before entering into the session, we want to know about the Laplace transform and what types of circuits can we analyze using this Laplace transform. First of all, if there is a circuit with any number of or any types of DC sources, it may be a dependent source, dependent voltage source, or dependent current source, whatever it is, and any number of resistance should be present in the circuit. We should able to analyze the corresponding circuit with the help of Laplace transform. And also, if it is a first order system or a second order system or first order circuit or second order circuits with source and without source, we able to analyze the corresponding circuit with the help of the Laplace transform. And also, if the circuit has the sinusoidal sources and it has any number of resistance, inductance and capacitance, then we should able to analyze the corresponding circuit with the help of Laplace transform. And one more thing, if it is a transformer or op amp, so we should be able to solve the corresponding circuit with the help of Laplace transform. But if it is a sinusoidal source exist, we go for only a steady state response. So the transient response is not able to solve with the help of the Laplace transform. So in order to find the Laplace transform at steady state, so we go for initial value theorem and final value theorem. So next, this is the definition of the Laplace transform. So Laplace transform of f of t, which is equal to f of s. So the general formula is integral of 0 to infinite f of t into e power minus st into dt. This is the general formula for the Laplace transform. The integral 0 to infinite represent the one-sided Laplace transform. Suppose if it is minus infinite to plus infinite, so we go for double-sided Laplace transform. But we are interested in the single-sided transform, so our limit is restriction into 0 to infinite. So from the use of the above formula, so some important functions, the Laplace transform of some important functions are given below. So therefore, the Laplace transform of del of t, here the del of t is nothing but impulse waveform or impulse response. So del of t into e power minus st into dt. So therefore, integral 0 to infinite, so del of t minus 0, it is some basic functions, or otherwise you write. So therefore, uh, the integral of 0 to infinite del of t into e power minus st into dt, which is equal to 1. This is the final Laplace transform of the impulse function. And similarly, if we take the Laplace transform of unit step function, the final value should be which is equal to 1 by s. So these are studied from the basic mathematics, so I need not go in depth. So the next one is the Laplace transform of e power minus at, which is equal to integral of e 0 to infinite into e power minus at into e power minus st into dt. So just you integrate this function and substitute the upper limits and lower limits. The final value should be equal to 1 divided by s plus a. And the Laplace transform of sin omega t, which is equal to omega divided by s square plus omega square. Suppose if it is cos omega t, then the Laplace transform should be equal to s divided by s square plus omega square. So these are the basic functions which we frequently used in our max. So I skip these formulas. So I move on to the next slide. So from the definition of the Laplace transform, so the various operations on the time domain functions and the corresponding results are tabulated here. So first of all, take some simple functions. So Laplace transform of some k1 into f1 of t plus k2 into f2 of t minus k3 into f3 of t. Here k1, k2, k3 are all constant. So in f1 of t, f2 of t, f3 of t are take some functions. So if I do the Laplace transform for the corresponding uh, functions here. So the formula is integral 0 to infinite k1 into f1 of t into e power minus st plus k2 into f2 of t into e power minus st minus k3 into f3 of t into e power minus st multiplied by dt. So here this dt is multiplied into every function and the corresponding functions are given here. Integral of 0 to infinite k1 multiplied by f1 of t multiplied by e power minus st into dt plus and so on. So here this integral f1 of t into e power minus st dt is nothing but so Laplace transform of some function. So therefore this is replaced by f1 of s. So the corresponding functions are replaced by like this k1 into f1 of s. I'm already told that this function, so 0 to infinite into f1 of t e power minus st into dt is nothing but so f of s. So here instead of f of t, so in the previous formula here f of t is present, so instead of f of t here f1 of t is present, so that this is replaced by f1 of s, and similarly it is replaced by k2 into f2 of s minus k3 into f3 of s. Sorry, I made some mistake here, it is k3 into f3 of s, I made a mistake. So similarly, the second one is f dash of s, which is equal to integral of 0 to infinite f dash of t into e power minus st into d of t. Here f dash of t is nothing but some differential function. So if the function is looks like this, so then use this formula. So integral of u into dv by dx into dx. So this is the format they given here. Dv by dx is nothing but f dash of t, and u is nothing but e power minus st, dx is nothing but dt. So the function is given like this, the corresponding function is replaced by uv minus integral of v into du divided by dx into dx. So this formula is called as integration by parts. So apply this formula to the corresponding function. So therefore the Laplace transform of d into f of t divided by dt, which is replaced by u into v. Here u is nothing but e power minus st and v is nothing but f of t. So therefore e power minus st into f of t, the limit is 0 to infinite minus integral of the limit is 0 to infinite v is nothing but f of t du by dx. It is here u is nothing but e power minus st, so which is differentiated like this. So the final answer should be minus s into e power minus st into dt. So this is the formula we converted from the integration by parts. So apply the corresponding limits. We know that e power minus infinite, which is equal to 0, and e power 0 equal to nothing but 1. So therefore minus f of 0. Okay, so already uh, minus is inside the bracket, so this minus goes outside, so minus into minus plus, so I put plus here, this is I take the s outside here, so yes, integral of 0 to infinite f of t into e power minus st into dt. So I already told that this is nothing but this function is nothing but f of s, so this is replaced by s into f of s minus f naught. So therefore I conclude, so it's the Laplace transform of some differential function which is replaced by s into f of s minus f of 0. It is for first order differential equation. If it is second order differential equation, so we have some other formulas, nothing but s square into f of s minus s into f of 0 minus f dash of 0. So this is the formula we use. So you studied the formula in mathematics, so I need not go there. So therefore, so in our circuit, so how we solve the Laplace how we solve the circuit using Laplace transform. So in our circuit we have so many number of resistance and so many number of nodes, loops. For example, take it may be a 3 loop system or 2 loop circuit, whatever it is. Okay, so for a given circuit, how we solve the corresponding circuit using Laplace transform. The first thing, there are two methods will be there to solve the corresponding circuit. The first one is, so write the set of differential equation in the time domain, and you should describe the relationship between the voltage and current for the corresponding circuit. Okay, so then you will apply KCL, KVL and some laws. For example, take mesh analysis, node analysis, whatever it is, or superposition theorem. So just you apply some equations. For your sake of understanding, I take here KCL, take KVL. I go for some mesh analysis, then I go for KVL equations. Okay, for the corresponding resistance, inductance and capacitance. So now you transform the corresponding time domain equations into a corresponding S domain equations or frequency domain equations. So therefore the corresponding V of t and I of t is replaced by V of s and I of s. If it is an inductor or capacitor, definitely there will be some differential equations will exist. Okay, so that differential equations is also converted into Laplace domain, and you process further, and finally you take the inverse Laplace transform to get V of t and I of t. So this is the one way to solve the corresponding circuit. The another way is, so first you take the Laplace transform the circuit elements, okay, and use the DC analysis. It may be a mesh analysis, nodal analysis, whatever it is. Just you use the DC analysis in the corresponding circuit to find V of s and I of s. So now you take the inverse Laplace transform to get V of t and I of t. In our further classes, so we solve a problem using these two methods. First we should formulate the time domain equations, and then we take Laplace transform and proceed there, and we take inverse Laplace transform and we get the answer finally. So similarly, if we directly apply the Laplace transform to the circuit elements and process to find V of s and I of s or whatever they has in the circuit, and finally we take the inverse Laplace transform in order to get the value of V of t and I of t. So we should see in the next class the problems. So now, how the elements, so in our circuits there are three basic elements will be there. The first one is resistance, inductance and capacitance. How these elements are changed from time domain to frequency domain. So the resistor in the S domain, how it is converted into S domain. So first of all, so in the figure A, they given it is a time domain circuit. So it is a resistance. The current through the resistance is nothing but I. The voltage across the resistance is V. So apply Ohm's law. So V equal to I into R. You take the Laplace transform on both sides. Here R is nothing but constant. So take R outside. So V equal to R into I. Here the capital V and capital I represent the Laplace transform of voltage and the Laplace transform of current. So this resistance element is simply replaced by like this. Here this voltage and current are in capital letters, which is nothing but the Laplace. It is in frequency domain. Okay, suppose if I go for an inductor in S domain, so we know that if there is a inductor is present in the circuit, then the inductor carrying initial current of I naught amperes. Okay, here I miss the I naught, so it takes some I naught ampere. The time domain equation that relates the terminal voltage through the terminal current is nothing but V equal to L into di by dt. So here uh, here the current is nothing but I naught ampere. Okay, so I missed it here, so which is nothing but I naught. So the inductor carrying the initial current of I naught amperes, and the time domain equations which relate the voltage to the current is nothing but V equal to L into di by dt. That means my inductor will oppose the sudden change in current. If I take this equation, and I put use the Laplace transform, so it is nothing but the differential function. So using the formulas given in the previous slide, so it is replaced by v equal to L into, okay, because L is nothing but constant, here function is nothing but I, so therefore which is equivalent to S into f of s minus f of 0, that is the formula. So therefore here it is replaced by S into I minus I of 0. So here I put I of 0 power minus, because we know that in transient response I of 0 which is equal to I of 0 power minus, okay, and so which is equal to SL into I minus L into I naught. Here I of 0 which is nothing but my initial current, so this initial current value which is equal to I naught, so therefore this is replaced by I naught, so therefore L into I naught. So this is nothing but my final equation of my voltage of the inductor in frequency domains. Now this voltage equation is replaced by like this. So here V equal to SLI minus L into I naught. Here I is nothing but my current in frequency domain. Here V is nothing but voltage in frequency domain. Here I naught is nothing but my initial current. So this is nothing but my source value, so that I put like here. So L into I naught which is nothing but my voltage source. So in order to accommodate this negative value, I put the source convention in this direction. Okay, you agree that? And this SL into I nothing but the drop across the inductor. Okay, so therefore the inductor is replaced by S into L, and the current through the inductor is nothing but I. The voltage across this element is V. So therefore the inductor is replaced by a series equivalent circuit which consists of some voltage source which is nothing but L into I naught, and the voltage drop is nothing but SL into I. Okay, so the same circuit is replaced by some parallel equivalent circuit, the same inductor. So then see this. Okay, so therefore here the same voltage equation we write, V equal to SLI minus L into I naught. If I want to find the parallel equivalent circuit, I want to find I, so I equal to V plus L into I naught divided by S into L. If I separate this, V by SL plus I naught by S, I naught is nothing but my initial current, so this is nothing but my current source, so this I naught by S is replaced by some current source. Okay, and V divided by SL is nothing but the voltage across the inductor which is connected in parallel with this V by SL is nothing but the current, okay, through the inductor, so which is given like this. SL is nothing but the impedance of the inductor, and V is nothing but the voltage across the inductor. So the total current is divided into two parts, which is not equal to V divided by SL plus I naught divided by S. So therefore my inductor is replaced by two circuit. It may be either a series equivalent circuit or parallel equivalent circuit. Okay, if it is a series equivalent circuit, for example take this, if it is a series equivalent circuit, for example take this, if they given a problem and in order to find the value of V, so if I want to find the value of the voltage, then I need to use this equation or this model. Suppose I want to find out the value of current, then I use this model. So depending upon the uh, variables I want to find, I use either a series equivalent model or either a parallel equivalent model. So depending upon the parameters, we should change the V or change the equivalent circuit of an inductor. So next, if I take, there is no initial current through the inductor, so from the previous there is no initial current here, that means here it should be 0. Okay, if there is no initial current means it should be 0, only my SL should be present. So similarly here, if there is value of I naught is 0 means it should be also 0. So if it is 0 means it is replaced by a short circuit. Okay, are you got it? So similarly if it is 0 means it acts as a open circuit. So in both the cases the impedance across the terminals AB which is equivalent to S into L, and the voltage across the element is V. So if the initial current is 0, my inductor is modulus S into L. In normal cases they put only L. If I model the inductor into the S domain or the frequency domain, it is replaced by S into L. The unit of SL is nothing but ohms. Okay, now if the capacitor is in S domain, if we take the initial voltage across the capacitor is V naught. Okay, therefore I equal to C into dV divided by dt. Okay, so use the same formula, integral by parts, and take the Laplace transform. So I equal to C into SV minus V naught. V naught is nothing but my initial voltage, which is equal to capital V naught. Okay, so I equal to S into CV minus CV naught. So this is a parallel circuit, because we know that in the inductor also we see about this I, which leads to the parallel circuit. So this circuit is replaced by like this. Here I equal to should be like this. SC into V is nothing but this is the current through the corresponding element, and CV naught is nothing but my initial current. Okay, in this aspect. So I replaced my capacitor in a parallel equivalent circuit, looks like this. So here it is nothing but my admittance, so it is mentioned in Siemens. So and here it is nothing but my independent current source, the value of C naught, and it is mentioned in ampere seconds, I hope. And the next one is the same equation is replaced by series equivalent circuit. Here we know the final formula in the previous slide, which is nothing but I equal to SC into V minus C into V naught. So therefore V equal to I plus CV naught divided by SC. So and I simplify this, it should looks like this. Here this V naught by S is nothing but my voltage source. It is given like here. So therefore this 1 by S is nothing but my is 0. That means my capacitance is replaced by like this. So therefore if the capacitance of value C is given, then it is replaced by 1 divided by SC in the frequency domain. So this is the final conclusion I made. So these are the elements we see in the corresponding session, and my resistance